Now let us revise some more properties of the D block elements. But remember, all these properties directly or indirectly related with the electronic configuration. Now the next is the D block elements are used in alloy formation. For example, brass is an alloy of copper and zinc. Copper and zinc both are from the D block of the periodic table. We have a stainless steel, which is an alloy of iron, chromium, and nickel. All three elements are from the D block of the periodic table. So what is special about D block elements? Now all D block elements are metals, have a comparable size. All D block elements are metals and have a lattice structure. Now due to their comparable size, one metal can substitute another metal in the crystal lattice and results in the alloy formation. So they are used in alloy formation. It is very rare to find an alloy without a D block elements. Next is the D block elements are used in the formation of interstitial compounds. Now why they are used in the interstitial compounds? What are interstitial compounds? Now D block elements are metals. Have a lattice structure. In which the unoccupied space is called a void or hole or interstices. And the small size, highly electronegative atoms negative elements or atoms can be fit into these interstices and form interstitial compounds and since all the voids are filled, the interstitial compounds are they are hard, they have a high melting point, they are good conductor of electricity, and they are used in abrasives. Examples are tungsten carbide, tantalum carbide. So these are some examples of interstitial compounds. The next D block elements and their compounds are used as catalyst. For example, this is a Haber's process for the manufacturing of ammonia. We used iron or iron oxide as a catalyst, and iron is from the D block of the periodic table. Another example is changing oil into fat using hydrogen gas. We use nickel or platinum or palladium, and nickel, platinum, palladium, they are from the D block of the periodic table. So again, most of the catalysts used commercially, they are either elements or they compounds from the D block of the periodic table, and they show catalytic properties. The catalytic properties are due to their ability to show variable oxidation states, and also due to the availability of empty atomic orbitals. Now next, the electropotential of the D block elements. This is another very important property of D block elements, E degree, standard electrode potential. Now electrode potential always refers to the reduction process. And as we know, common oxidation state of the D block elements, or especially the 3D series elements, is +2. So we write the reaction like this: M2 plus aqueous plus 2 electrons is in equilibrium with M solid, and the E degree is equal to M2 positive oblique M. And this E degree value depends on three factors. The first one is the enthalpy of atomization or enthalpy of sublimation. Second, it depends on the ionization enthalpy. And the third, it also depends on the enthalpy of hydration. Now, since delta sublimation and ionization enthalpies do not follow regular trend in the 3D series, so therefore we have irregular trends in the E degree values. This is very important point. Now next point, in the 3D series, only this electropotential of copper is positive, and this is due to a low hydration enthalpy of copper 2 plus and the high sublimation enthalpy of copper and high ionization enthalpy of changing copper to copper 2 plus. The next point is, if you are given this reaction in which the metal is showing two different oxidation states, for example M plus M minus n electrons to give, or is in equilibrium with n positive, where m is greater than n, then E degree value and the stability of the plus n oxidation state directly related, and the stability of plus m oxidation state inversely related. For example, if these values are given, chromium 3 plus, this is another very important question, minus 0.04 volts, E degree value of Mn3 plus to Mn2 plus is plus 1.50 volts, and E degree value of the Fe3 plus to Fe2 plus is plus 0.77 volt, then the increasing stability order of the plus 3 oxidation states is this. Chromium 3 plus is the most stable because it has a half filled T2G3 configuration. Next comes iron 3 plus, which has a half filled 3D5, and the least stable is Mn3 plus, which has a configuration of argon 3D4. The next point is that the D block elements are used in the complex formation. In the complex formation are due to, first point, due to their ability to show higher oxidation states, due to their small size, and the availability of empty atomic orbitals so that they can accept lone pair from the ligands. Atomic orbitals. Examples are like we have a FeCN6 4 negative. We have this Nestor's reagent, it's a complex of mercury. We have a brown ring complex, which is a complex of iron. So these are some examples of the complexes formed by the D block elements. So these are some properties of the D block elements.